Hi everyone. So we'll talk with Adrien about the solution of the GreHack challenge. So this challenge was composed of 4 levels: one of steganography, one of cryptography, one of network, and the last one was a reverse engineering challenge. And actually, all the levels were interspersed with five cryptography challenge, easier ones that can be solved for most of them with a pen and a paper. So let's start with the first old crypto challenge. So it's just a text written with a strange alphabet, and actually this level is very simple. You just have to it's just a text encoded with a custom web font, and if you read the HTML code of the page, you directly get the validation flag. So now for the first real challenge, it was called AZTEC challenge, and it's taken from an old game, and it was a steganography challenge. I don't think it's a good solution to start a challenge with a steganography challenge, and actually I don't think it's a good idea to put a steganography challenge. So it was an animated GIF from pictures taken from the old AZTEC challenge game. And what you had to do is to extract frames from the animated GIF. For example, with ImageMagick. Actually, it was simpler with ImageMagick for a certain reason, but it's fine. And one of them is peculiar. There's some kind of QR code inside. So if I zoom on it, it's not a QR code, it's an AZTEC code. Maybe you never heard this name, but it's mainly used, it's widely used, for example, in transport tickets. And so I already take this train, so you cannot. And if you zoom on it and try to decode it with an online decoder, you get a message saying that you're close and dig a little more. So welcome to steganography. And if you look at actually it's a GIF image, and what is special with GIF images is that you can specify a color palette. And if you apply a random palette on the image, you see that the AZTEC code is not composed of 2 colors, black and white, but actually of 4 colors. There are 2 white and 2 black, very similar. And if you modify the palette a bit, you see a new AZTEC code appearing, and this one has got a flag. I think this part has blocked a lot of people. I hear voices from there. And yeah, I liked it more or less. Let's go again with old crypto challenge. So this time the text were very small to decode, and there was a hint. Maybe you saw this hint outside. So it's like an affine function. It's a bit tricky because the affine function, it looks like the slope is equal to 1, so it so in like a Casa cipher, but no, it's a affine cipher. So affine encoding is like y is ax plus b, and if you want to encode a given message, you take, for example, GreHack. You take a equal 17, b is 20. You convert each letter to a number. You apply the affine transform. You get the result modulo 26, and you convert this result to letters, and you get the encoded text. So now, how to decode this message? You apply the inverse transformation. So for this, you don't know the values of a and b. So for b, there are 26 values. For a, there are 26 values. Actually, only 12 values, because the value of a must be coprime with 26, so that it has an inverse. So you have 312 something like possibilities. You read all of them until you get the flag, which is a affine romance. Actually, there's a more clever solution. you can guess the text starts with affine. That's how I did it. It's maybe not obvious, but so this means. I won't say what it means. You can solve it by yourself. The next challenge was a network challenge, and it was a bit confusing because it was only composed of a text file. So you can see strange things above, like a phone number, AZTEC, and a phone number. It's actually the phone number of the CEA. At the beginning, here is a German. It's a German text, willkommen. So it looks like a connection on a server. And yeah, I didn't know the CEA talked German. So at first, to solve the challenge, I thought we had to call this number. And finally, I didn't try it. So it's actually 80 commands for ACE modems, which were modems for analog phone lines. And so I used to send PPP packets. And these PPP packets are given there in a printable format that was used for to transmit PPP frames on asynchronous links, which is the case for analog phone lines. And the only description I found was on the MSDN. Once you get this, you understand that this is a PPP connection, and the authentication chain is done with a CHAP, challenge response. You extract the challenge and the response, and you brute force. That doesn't work. And actually, if you remember that the connection message is willkommen, you brute force again with a German dictionary, and this time that works. And the solution was nuclear Waffen. This one was a bit confusing. There's a binary string with a long hint. I thought I understand nothing about the hint. I think the hint is July. July, you must think seventh month of the year. So okay, 7. So you take the bits 7 by 7, and you get a printable string, which is modern encoding. Okay, something a bit more complicated here. I have not so much time. So let's explain quantum cryptography in 45 seconds. So Alice wants to send a message, a bit string to Bob. She converts the bit string to qubits, and Bob manages to receive some of the qubits, not all of them. Okay, he then sends back a few bits he received to Alice, and if they are correct, if they say, okay, the connection is correct, we can talk. We have exchanged a key. Oh, no. Now, if an attacker, Eve wants to eavesdrop the connection, she tries to intercept all the qubits sent by Alice to Bob, and there are high probability that she will perturb the state of the qubits sent, very high probability actually. So if Bob wants to verify the qubits he received with Alice, that will not work. That's all we have to understand for this challenge. So the challenge is actually the BB84 scheme, which was the first scheme designed for quantum key exchange, and it's used to exchange an IAS key, which is needed to decrypt the file, which is a flag. So many bits are exchanged. The first one are sent to make sure the channel between Alice and Bob is secure, and the other ones are the ones which contain the IAS key transmission, and we don't have them. We have to guess them. So we'll see after how to do this. There's actually not one capture, but 11 captures. And if we look closely at the 11 captures, we see that 10 of them are actually eavesdropped by Eve. They are incorrect, so we can drop them. And now we know which capture contains the real IAS key. but we don't know the bits which are exchanged for the ASCII as they are not present in the transmission. So for this, we look at the implementation, and we see that they are generated with the LFSR. And this an LFSR has a good property is that with if you know a part of the output, enough bits, you can compute the whole internal state of the LFSR, and so that you can generate a long output. So hence we can retrieve the output bits. So for this, there's an algorithm which is known as Berlekamp Massey algorithm. I didn't have an implementation for it, so I didn't use it, and I managed to brute force the LFRC and the polynomial. Actually, it wasn't made to be possible, but there's a kind of bug in the implementation. And with this, you get the sequence of bits of Alice and Bob. You can compute the ASCII and decrypt the flag. You decrypt the flag, you obtain the barcode. Must remind you the challenge last year, and you get the flag, and it's over. And the last challenge I will talk about is elementary my dear, which are stickmen drawn manually. You can see the lines with a paper, with a pencil. I don't know who did this. So this is a non-cipher. It has been taken from a Sherlock Holmes novel, The Adventure of the Dancing Man. You can find the text, the whole text online, and it's a monoalphabetic substitution. You get the alphabet here. So what I did is that I printed the text and took a pencil and decoded the letters one by one. You get a question, who uses this code, who sends these current messages, and if you want the solution, I won't spoil it, so yeah, read the novel. I will let now Adrien present the two last challenges.
Thank you, Jean-Baptiste. So the next challenges was called over-engineering. It was an archive with first a Rust file and 337 binaries. So if we just take a quick look at the binaries, we see that there are 5 different architectures and operating systems. And if we take a look, fast look at the Rust file, basically it takes integers as input and generates a key. So it looks like we have 100 of crack means to crack. So if we take the first one, we open it in IDA, and we see what it looks like. So basically it just takes an input on the command line. It will reserve a page of memory, decode some shellcode, and set this page as executable and call the shellcode. If the shellcode returns 0, it's fine. If it doesn't return 0, it's not fine. So what we basically need to do is to give an input to this program so that the shellcode generates 0. So first thing we need to do is to jump the shellcode. So one trivial thing to do is to break after it's decoded that you dump it. If we open it in IDA, we see that we have got 4 conditions that are computed from the input. If these 4 conditions are valid, we've got some computation, and this computation returns the value. If one condition is not good, it's returned -1, and so it's not the good value. So if we put it in a small pseudo C code, basically the shellcode is like that. And so the goal is to find a value such as this function returns 0. And we got to do this automatically because we have 100 of binaries, so we don't want this to do by hand 100 times. So one solution is to transform this into an expression using symbolic execution and use Z3 to solve this for us. So if we put it all together, for each binary we need to unpack it, end up this shellcode, and then we need to do the symbolic execution of this shellcode, and then use Z3 to solve this. We've got to do that for 1,000 binaries, for 6 OX architectures different, so we need to automate the whole thing. Or we need 1,000 people to do that, but we don't have 1,000 people. So unpacking binaries, like you can do this with many different things. We did this using MIASM for Linux binaries. There's some bugs which works for ARM, ARM64, and so on. Same tool can work for your platform, so it's quite good. But it just doesn't work with the Windows binaries because you need to handle all the Microsoft CRT runtime, and it just doesn't work. So you've got this really nice way to do it. You can use wine and GDB and the GDB script and you break on a virtual protect and you dump the shellcode, and that's it. So now we're going to see how we can do symbolic injection with Miasm. So I made a small demo to show you that it's easy to do. So let's take an easy function. This one, I've got some time. How many time do I have? Wow, that's a good one. Okay, now. Sorry. Okay, so we run Miasm. Okay, we import stuff. This is our shellcode. It's just a function. This one, which just makes v plus 5. Okay, it's really simple. So first thing we need to do, we disassemble the assembly using Miasm. So it's LEA, RX, LGA plus 5. So that's v plus 5. First, and then we convert it to the Miasm IR. So basically it says it will convert this assembler instruction to symbolic expressions, equivalent symbolic expressions. And so it says RX is equal to RGI plus 5. So that's basically what we do. And then we initiate a symbolic state. We create a variable which is v, which is our input, and we say, okay, RGI is equal to our symbolic input. So it's basically the symbolic state is just this at the beginning. And then we symbolically emulate our IR, and then it says here in the end, okay, RRX is equal to v plus 5. So that's fine. And what we do in the end is we translate these expressions to that3, as that3 is the solution, and so 1 plus 5 is equal to 6. Here the solution is 6. And that's fine. So that's an easy one. Sorry. Now let's see how we can make, because we have branches, so let's see how we can make this symbolic execution with branches. So that the second more complicated example. This one. So if we compile this with Clang or GCC, it will optimize this with a cmove because maybe it's better anyway. So we've got this assembly here. Then we disassemble with Miasm, so it's basically the same assembly we had, sorry. Then we translate it to the IR, so it's a bit more complicated, but what we can see is we've got two constants here, and then we've got a branch. It says, okay, if this condition is okay, I will execute this code, or I will go right there. And so what it says in the end is that RX is RX plus RGI. RX is either this constant, or RCX, which is 5. And so if we still initiate our symbolic state, we run it, and it says, okay, RX equals minus 7, RCX equals 5, RGI equals V, so that's fine. And it says the next instruction depends on the condition, because we are actually here, so that's normal. And so what we need to do now is to symbolically execute every branch, every possible branch, and say, okay, the expression is a nested, are nested conditions, and we give you thing the end. So it's a recursive algorithm, which is coded here. And in the end, if we run it, it says, okay, the return value will be a condition, and from this condition, you can have v plus 5 or v minus 7. We translate it to that3, and we solve it, and that's it. So that's basically what we did for every shellcode. So that's, and we need to make this cloud platform, because here the IBI is really depend on the architectures. For instance, on Linux, the argument is RGI. On Windows, it's RCX. On ARM32, it's using 2 registers for 64-bit integers and so on. And you've got a small gotcha. Yeah. With ARM constant pools, because in ARM32, you can't put 32 or 64 bits in instructions, so the constants are within the code. So you need to load your code within your symbolic states, so that they can be actually read by the symbolic emulator. So some stuff about the performances of that. So we run this in parallel on our computers, and so basically it runs fine for ARM64 and x86 64. And we've got some issues with x86 32 bits. So we've got like 20 minutes to crack me, and so we stopped this because it's really started to take too much time, because we need to figure out why. So the issue that there's a lot of cmove in these x86 codes, and we saw Miasm generate branches for the cmoves, and so we have really a complex graph in the end, and so we have really a lot of branches to simulate, and this is what it takes a lot of time. So one idea is to say we need to remove these small branches as soon as possible, and one way to do it, which is not a good way but it works, is to modify the way Miasm translates to cmove instruction. It's actually not really a good idea. You can read this pull request to know why. I can explain this now. Anyway, if we still do that, we got really good numbers here, so they are really better, like it's only on average of 30 seconds to fix a crack me. What can be interesting is still to try to optimize this. Actually with PyPy's it's actually worse. We have a Manticore workshop later, maybe it's gonna be better, I don't know. Anyway, so if we take for instance this crack me, it goes from 20 minutes to 45 seconds, so it's actually a pretty good optimization. And so in the end you need to compute your flag, so if you catch the rest of code, it's really an over-engineering stuff just to compute ZORs and share 265, 56, sorry. And so you compute this, it gives a key for SHA-20 algorithm, and it gives you a French message, so if you're not French you don't understand. And the final flag is actually the key, and that's it. So the last challenge was called online numbers, so it starts with a text file which is like that. This looks like ASCII encoded text in hexadecimal, and we've got this substitution table, two-dimensional substitution table. So we've just decoded the hexadecimal, we end up with this ASCII text. So you just have like this, and if you have some, like, I don't know, magic in your head, you can say, okay, this is actually dates. And this character is represented by 2 dates. Alright. So actually what gives us the idea of this like character, you say, okay, maybe this is one character and blah blah blah. So each date has a weekday, and the weekday you need to map the 2 weekdays using the substitution table, and it gives you a character. If you do that on the whole text, you get the one got code today, so the text in frac from the mentor, and that was the flag. You had to find the author of this text, and you had to write it down like that, especially because it was written in the challenge. You need to write it lowercase without space. And that was it. Thank you. If you have questions.
Questions? No?
Huh?
Okay. So if you don't have questions, let's thank Jean-Baptiste and Adrien again.